Hello, I am Sunita. Welcome to my class. Here I am going to discuss GPSTR science topics according to the syllabus. Here I am going to discuss one of the most important topic, measurement, unit and dimension. Let us start the class. Introduction to units and dimension. Every measurement has two parts. The first is a number and the next is a unit. It is represented by Q is equal to NU. This one we will call it as a physical quantity. Physical quantity, it has two units. N is a number and U is the unit. N it will represent the number of times. U it is the unit. Always the unit, it will compare the physical quantity. For example, the length of an object is 40 centimeter. Here 40 it will represent the number, otherwise number of times. Centimeter it will represented by unit. Centimeter it will compare the quantity. The number expressing the magnitude of a physical quantity is inversely proportional to the unit selected. If n1, n2 are the numerical value of a physical quantity corresponding to the units u1, u2, then n1, u1 is always equal to n2, u2. For example, 2.8 meter, it will be equal to 280 centimeter here. If any quantity, if it is length is 2.8 meter, you can express in terms of centimeter also. Then here 2.8 it will represent a number, otherwise number of times. It will be converted into 280. Then here meter it will be converted into centimeter. But the product of these two, 2.8 meter and 280 centimeter, product it will be remains constant. Then 6.2 kg it will be equal to 6200 gram. Here also you are converting the unit from kg to gram. Here also the product of units, it will not change, it will be constant. Let us discuss in detail what is meant by a physical quantity. A quantity which can be measured and expressed in the form of laws is called as a physical quantity. A physical quantity is nothing but you can easily measure and you can express in the form of a loss. This quantity we will call it as a physical quantity. Formula for physical quantity is magnitude into unit, n into u, where n is the numerical value, u is the unit. I already mentioned n it will represent the number of times of a unit, u is unit. Unit it will compare the quantity. As the unit u changes, the magnitude n will also changes, but the product of nu will be remain same. This also I already explained. N1 u1 it will be equal to n2 u2, always it will be a constant. If you are converting unit from one form to another form, after converting the product of magnitude and unit, otherwise numerical value and unit, the product it will be always constant. Let us see next one, fundamental and derived units. What is meant by fundamental units? Any unit of mass, length, time in mechanics is called as a fundamental, absolute or base units. Name itself, it is indicating fundamental units or base units. These units, they will not change. The value of the unit, it will not change. Otherwise these values, they will not depend upon the any other units. These are the absolute and also base units. Length, mass, time, temperature, these are the few example of a fundamental units. Other units which can be expressed in form of a fundamental units are derived units. Here derived units are derived from the combination of fundamental units. Then here system of units, a complete set of units both fundamental and derived of all kinds of physical quantities is called system of units. There are four system of units. We only have to study the SI system. First one is CGS system, second one is MKS system, third one is FPS system, fourth one is SI system. This fourth system is very important. This SI system of units we have to study in detail. Already I mentioned fundamental units, they will not depends upon the any other quantities, they will be independent of the other physical quantity. Here you can see the 7 fundamental physical quantities and their name of the units and their symbol. First one is, first fundamental physical quantity is length, then it is expressed in terms of a meter, then assigned symbol it will be, the symbol it will be small m. Then mass, second fundamental quantity mass, name of the unit is kilogram, then it is represented by kg, capital K, G is small here. Third fundamental physical quantity is time, it is name of the unit is second, it is represented by small s. Then fourth one, electric current, it is represented by ampere, then its symbol is capital A. Fifth one is temperature, then name of the unit is Kelvin, it is represented by capital K. Next one, amount of substance, name of the unit is mole, it is represented by MOL. Here M it should be capital. Then next one, luminous intensity, name of the unit is candela, then it is represented by capital C, small d, CD. These are the 7 fundamental quantities. These quantities are very important, this one you have to remember. Derived quantity, the quantities that are derived using the fundamental quantities are called derived quantities. Derived quantities are obtained by the combination of fundamental quantities. Derived quantities we can express in the form of a combination of fundamental quantities. The units that are used to measure these derived quantities are called derived units. For example, force, velocity, density, heat, power, energy, momentum, acceleration. These are the few examples of a derived quantities. Let us discuss in detail what is meant by a derived units. Let us consider few examples to understand the concept derived units. First one is density. Quantity is density. Density formula is mass divided by volume. Then its derived unit is kg per meter. Here kg is the fundamental units, meter is also fundamental unit of length. Then the combination of fundamental units it will gives derived unit. Then next one is quantity is velocity. Formula is distance divided by time. It is indicated by derived units meter per second. Then third one is acceleration. Formula change in velocity divided by time. Derived unit meter per second square. Then fourth one area. Formula is side into side. It is expressed in SI, derived unit is meter square. Then here you can observe the derived unit is a combination of fundamental units. Here you can see the fundamental units are kg, meter, second. These are the fundamental units for mass, length, time. Therefore, derived units are obtained by the combination of fundamental units. Let us discuss the difference between fundamental units and derived units. Fundamental units are all those units which are independent of any other units, including themselves. Fundamental units exist individually, they will not depend upon any other physical quantities or physical unit. Therefore, fundamental units are independent of any other units, even including that unit itself. Derived units are all those units which are obtained by multiplying, dividing one or more fundamental units with or without introducing any other numerical factor. Derived units, already you know, derived units are obtained by the combination of fundamental units. Either you can multiply or divide the fundamental units. Then here in the case of derived units we will not use any numerical factors. Then next one, fundamental units cannot be further reduced to elementary level. In fact, these are elementary units. Fundamental units or basic units you can't devise, otherwise you can't reduce further into elementary level. These are the basic units. Next one, derived units can be reduced to its elementary level, which are composed of fundamental units. Derived units are the combination of fundamental units. Therefore, the derived units you can be reduced to its elementary level. Third one, fundamental units cannot be expressed in terms of derived units. Fundamental units are base units. You can't express fundamental units in any other forms. Third one, derived units can be expressed in terms of fundamental units. Derived units are the combination of fundamental units. Therefore, derived units you can expressed in terms of a fundamental units. Fourth one, only 7 fundamental units exist in metric system or SI system. Already you know 7 fundamental units exist in SI system. Fourth one, there exists a large number of derived units in metric system. Derived units, you are deriving from fundamental units. Therefore, a large number of derived units it will be exist in metric system or SI system. Then fifth one, 7 fundamental units are meter, kilogram, second, Kelvin, mole, ampere, candela. These are the 7 fundamental units. Few derived units are Newton, Joule, Watt, Volt, Pascal, Celsius, etc. These are the few difference between fundamental units and derived units. Supplementary or physical quantities. Beside the 7 fundamental physical quantities, 2 supplementary quantities are also defined. They are plane angle and solid angle. Let us discuss in detail what is meant by a plane angle. Is the angle between two intersecting straight lines measured in the plane of the same lines. It is a dimensional physical quantity measured in either degree or radian. When two lines, when they are intersecting each other, then it will form an angle. This angle we will call it as a plane angle. Here this is the circle, then this is the arc of the circle, then this is the radius of the circle. Then plane angle, it is represented by theta. D theta, it will be equal to arc divided by radius, ds divided by r. Then SI unit of plane angle we will express in terms of degree or radian. Normally radian we will represent it in terms of RAD. Short form of radian is RAD. Then next one, solid angle. Solid angle, plane angle is a 2-dimensional angle. Solid angle is a 3-dimensional angle subtended by any object at a certain point in 3D space. It is the ratio of area and the square of distance. Hence, it is a dimensional physical quantity which is measured in SI unit of steradian. Here, solid angle is a 3-dimensional angle. Let us consider the example cone. This is the cone. Then the intersection of lines, it is form an angle. This angle we will call it as a solid angle D. This one. Then the solid angle is given by normal surface area divided by radius. Radius square normal surface area, this is in the form of a cone. This surface area we will call it as a normal surface area divided by radius square. Then solid angle, it will be equal to dA divided by r square. Then here dA, it will represent a small area divided by r square. The SI unit of solid angle is steradian. You have to remember this is the short form of steradian is SR. Then these are the 2 important supplementary physical quantities. These are the basic fundamental physical quantities. Let us discuss in detail dimension of a physical quantity. Dimension, we will consider 7 fundamental units, 7 fundamental physical quantities. Here, our convenient as a universal symbol we will use for 7 fundamental quantities, physical quantities. We will use some symbols. That symbol, it is used to represent dimension of a particular physical quantities. Here consider 7 fundamental physical quantities here. For length, we will use the symbol L. L, it is used to represent a dimension of a physical quantity for L. Then mass M, capital M. These you have to put inside a square bracket. Then third one, time. Time, we will use the symbol T, capital T. Then temperature, we will use Kelvin. Kelvin is the SI unit of temperature. We will use one symbol K or theta. Both also we can use. Then fifth one, electric current. SI unit of electric current is ampere. We will use first letter capital A. Luminous intensity candela, we will use only C to represent a dimension of a luminous intensity. Then amount of a substance, the SI unit of amount of substance is mole. In that one we will use only mole, M-O-L. These are the 7 fundamental physical quantities we will use. These quantities, to represent these quantities in terms of a dimension, we will use these symbols. Therefore, here dimension of a physical quantity, when a derived quantities is expressed in terms of a fundamental quantities. Here derived quantities, already you know derived quantities are the combination of fundamental quantities. It is written as a product of different power of the fundamental quantities. Here already I told these symbols we will use to represent a dimension of a physical quantities. Then these symbols, if we use in terms of a power, then that one we will call it as a dimension of a physical quantity. Then what is mean by a dimension? The power to which the fundamental quantities must be raised in order to express the given physical quantity are called its dimension. Here you are having 7 physical dimensional quantity. If you raise the power to which the fundamental quantities to express the given physical quantity, we will call its dimension. Let us discuss in detail dimension of a physical quantity with an example. First one, area. The formula of a area is length into breadth in the case of a rectangle. Then length we will measure in terms of meter. Then breadth we will measure in terms of meter. Meter into meter, it will give meter square. Then L is the symbol used to measure the length. Then here L power 2. L into L we will consider L power 2. Then normally in dimension we will use 3 powers, 3 symbols in terms of a power. One is mass, second one is length, third one is time. If you are not having any dimension for that particular, we will raise the power 0. In the case of area, M, dimension of area in mass, it will be 0. Dimension of area in length, it will be power 2. Then dimension of area in time, it will be 0. Second one, volume. The formula is length into breadth into height. All the 3 we will measure in terms of a meter. Then m into m into m, it will gives m cube. Then here dimension of volume in terms of length is 3, L to the power of 3. Here mass also 0, time also 0. Time also 0 here. Therefore, if we represent in terms of MLT, then dimension of volume in terms of M is 0. Then dimension of volume in terms of L is 3. Dimension of volume in terms of time is 0. Third example is mass density. The formula is mass divided by volume. Mass we will represent in terms of kg, then volume M3. Then mass we will use the symbol m to the power 1 divided by volume L to the power of 3. Then here mass to the power of 1, L if you shift to the numerator, then it will become minus. Then L to the power of minus 3. Then here m to the power of 1, L to the power of minus 3, then t to the power of 0. It will give the respective dimensions. The dimensions of density in mass is 1. Dimension of density in length is minus 3. Dimension of density in time is 0. Normally, when we are representing the dimensions, we will consider only the power of the respective symbols. Next one, velocity, speed, both are same. Velocity is nothing but displacement divided by time. Displacement also we will measure in terms of length. Then time also, time only in terms of second. Then here L to the power of 1. Here also if we shift t to the numerator, then t to the power of minus 1. Then here mass is 0, mass power is 0, m to the power of 0, L to the power of 1, t to the power of minus 1. Then dimension of velocity in mass is 0, dimension of velocity in length is 1, dimension of velocity in time is minus 1. Then next one, acceleration. Acceleration, change in velocity divided by change in time. Velocity also we will measure in terms of meter, change in time, second into second, meter square. The SI unit of acceleration is meter per second square. Meter we will use the symbol L, then time t to the power of 2. Then here m, dimension of m is 0, m to the power of 0, then L to the power of 1, then t to the power of minus 2. Dimension of acceleration in mass is 0, dimension of acceleration in length is 1, dimension of acceleration in t is minus 2. Then here acceleration due to gravity, it will follow the same dimensions only. Here I am given list of few important dimensions of complete physics. Here I given in terms of slides. You have to read that one. You have to remember. Listen here. Here I provided a list of quantities that they have the same dimensions. Applications of dimensional analysis. First one, to find the unit of a physical quantity in a given system of units. To find the unit of a physical quantity, we can use the dimensional analysis. Second one, to find dimension of a physical constant or coefficient. To find the dimension of a physical constant or coefficient, we will use dimensional analysis. Then third one, to convert a physical quantity from one system to another system. You know, physical quantity you can convert from one system to another system. The conversion of physical quantity from one system to another system, this dimensional analysis, it will help. Limitations of dimensional analysis. First one, if dimensions are given, physical quantity may not be unique. Second one, numerical constant having no dimensions cannot be deduced by the method of dimensions. You know, numerical constant, it will not involve in the limitations, it will comes in the limitations of dimensional analysis, because in dimensional analysis it will not indicate the numericals. Third one, the method of dimensions cannot be used to derive relations other than the product of the power. For example, s equal to ut plus of at square, then y is equal to a sine w theta. In this formula, we can't easily find out the dimensional analysis. Then next one, fourth one, the method of dimensions cannot be applied to derive formula consist of more than three physical quantity. This dimensional analysis we can't derive formula consist of more than three physical quantities. Thanks for listening my class. Send me your valuable feedback. Thank you.